Okay.
All right.
Okay, so I'm going to let us go to the board and I will explain to you how the so-called magic happened. Okay. Continuing from where we left off yesterday. See, the whole of machine learning is something you learned in school, but we all thought was useless. What is that thing? You all remember f of x, g of s of s, the domain of f of s, the range of f of x, the inverse of f of s, and we're sick and tired of elective math teachers. What is all this f of s? What is this g of o of s? What is this inverse of f of s? Well, that one put food on my table. Yes, that is what put food on my table. F of x is what feeds me. Okay, how does f of x apply here? See, can you challenge me, especially for the physicist here? I can boldly tell you that if you give me any two numbers, except those special numbers like 0 and 1s, which we already have mathematical, like special mathematical meanings for them, I can tell you that if you give me any two numbers, I can tell you how one is related to the other. It's just a matter of performing some calculation. How do I know? Yes, I can tell you that there is something I can multiply with 5 to give you 6. Who can tell me what that thing is? There is a number in this world. When I multiply it with 5, I will get 6.
6 over 5.
Genau. Exactly. 6 over 5 multiplied by 5 is going to give me 5. And this is all that the model is doing. Okay, so you have your data, which is X. Now, your model, if you think of a machine learning model, think of it this way. F of X is equal to Y. Yesterday, I told you that it's a giant matrix. This one is not a giant matrix yet, but there's a rather simple linear regression. But when we get to bigger things, it's going to be a giant matrix. Now, f of x is equal to y. What is this supposed to mean? Well, it is telling you that, think of the f as a black box, okay? As a black box. So this is your f of x, the function. You put in x, something happens to that x, it gives you y. Before I explain the mathematics to you, there is something called data set. There is something called features. I need to explain that to you. You see, when you have tabular data, let's say we are measuring people's height, we are measuring people's weight to determine whether they have diabetes or not. Okay, so H for height, W for weight, D for diabetes. Each row is called an instance of the data. Instance. Because it's encodes the information about a particular person. We know the height of the person, the weight of the person, and whether the person has diabetes or not. Each column is called a feature. It's called a feature. The whole table is called a data set. So when you hear instance, how many instances do you have? I'm basically asking you, how many number of rows are there in your data set? How many features are there in your data set? I'm asking you, how many columns are there in your data set? Then I can ask you, which features are you using for the training? You see, in Olatunde's question, they have a high dimensional data, maybe 10,000 columns. But not all these 10,000 columns are important to the discovery of the pattern. Maybe it's just 10 of them and the rest is noise. So you don't just throw all these 10,000 to a model. I told you yesterday that models are lazy. It's like electric current. It takes the path of least resistance. What is the easiest thing a model can do? Memorize. And that one models will do perfectly. That is why most of the time people train models, is doing well on their computer. They put it out there and the model will see donut and tell you that it's a cat. Because it has, instead of learning, it has memorized. And there are ways of knowing whether your model has memorized or has actually learned. We get there. So if I ask you which features, Eric, did you ask a question?
No.
Okay. If I ask you which features you are using for the training, I'm asking that maybe you have several features, several columns, but it's not all these columns that you are using for your training. So tell me which features you are using for your training. These are things that you need to know as a machine learning expert. Now, each row, we usually indicate that with xi, so x1, x2, x3, because each x is an instance. So each x is a vector. Then we use capital X to represent the entire matrix. Okay? So in this data set, if I'm trying to use height and weight to predict whether you have diabetes, then height and weight becomes my X, and your diabetic status, Y, here is what I'm trying to predict. I can represent the fact that you don't have diabetes with 0 and 1 for you have diabetes. Then we throw this to a model and the model is going to learn from it. Now let's talk about how learning is happening. So I wrote what some of you hated in school and you thought, now that I finished BC, I can tear my Aquila. I'm never going to meet it again. Here you are. F of X is equal to Y. What is going on here? You see, I gave you two numbers. Degree Celsius, degree Fahrenheit. And just as I proved to you that I can multiply something with 5 and get even 0.1. This is also true. There is something I can multiply to 5 and get 0.1. This is mathematics. You can't debate it. So the first assumption the model makes is, well, there is something I can do to degree Celsius to get degree Fahrenheit. Please, it is very important that you understand. So if you don't understand anything, stop me immediately before I get deeper. Are we all clear? Okay, so we are clear. The model assumes that mathematically, there is something I can do to degree Celsius to get degree Fahrenheit. Then comes another enemy from high school, equation of a line. Y is equal to mx plus c. Which means if I have a plot like this and I draw a line, we draw the x on the x-axis, our y on the y-axis. And what we're basically saying is that there is a relationship between our coordinates, how x is related to y. And the way we find that, or the relationship involves two unknowns. We need to know the gradient of the line, which is m. This is your gradient. And this is your intercept on the y-axis. That is where the line meets the y-axis, okay? If I change these two numbers, it will change the shape of the line. For example, if I say that y is equal to 0x plus 3, this is basically a line like this. on the y 3, and it's like this. This is this line. Why? What I'm saying is this line doesn't even depend on the gradient. 0x. So the gradient being 0 zeroes out the x completely. So this is a line where no matter what point you put on the x-axis, you get 3. You see, when the gradient of a line is 0, it means the line is horizontal. It is straight horizontally. And if your gradient is nearing 1, it gets more vertical and vertical and vertical. So I can either change the intercept on the y-axis. If I change the intercept on the y-axis, like here, and I keep the gradient constant, the inclination of the line is going to change. If I maintain the intercept on the y-axis, but I increase or decrease the gradient, the line is still going to change. Who feels like crying now? Okay, nobody feels like crying. That is great. So now it becomes a problem to the model. The first assumption is the model will say, dude, degree Fahrenheit is equal to something times degree Celsius plus something. I'm going to say B. So over here, the B is the intercept on the y-axis, and the M is the gradient. You see, these are just two numbers. Tomorrow we'll be dealing with multivariate regression, where there are multiple things. Then the math will get a bit more complex. So it assumes this. Okay. So now our model is going to say, instead of thinking that it knows the correct way to convert from degrees Celsius to Fahrenheit, it will say F prime is equal to, I multiply the degree Celsius by something and I add something to it. The reason why it has to add the y-intercepts, the physicist here, why isn't it enough to just multiply it by the gradient? Why do we have to add something? You see, it is not always possible to achieve this through simple division. Sometimes when you divide, you will not have very accurate number and you need something to add to get the correct answer. That is why there is the plus to make up. So where the plus is not needed, your intercept will become 0. Okay. So you see, we gave our model our x's, like in our code, this was x, which was degree Celsius, and our y was degree Fahrenheit. Okay. So the model will say, I'm not very sure. So let me say F prime instead of F. It is equal to MC plus B. Now it is the job of the model to find everywhere I put a question mark. So M and B becomes what is known as the parameters of the model. And now we need an algorithm to help us find these parameters. I have taught Mohammed how to code that algorithm from scratch. So maybe I can hand over for Mohammed to teach you. Mohammed, will you?
I don't think so. I'm going to do it how the way I'm doing actually. Yeah,
it's fine. It's fine. So
I have a question, please.
Okay, yeah, come ahead.
Just something just came in mind regarding the y-intercept.
Mm-hmm.
So I was thinking that, is it kind of definitely, even when the x value, as in the independent, is 0,
mm-hmm.
it indicates what value the dependent will be when the independent is 0. So
now,
in all cases, there should be, unless there isn't, when this is 0, then the other is also 0.
Exactly. Sorry, when I say genau, that is it's a German word. it has stuck to my tongue, but I mean exactly. So that is the point. The question is, what is your y when the x is 0? And that is why I said it is not always the case that you can achieve that through simple division. You get a point, and you have actually given a better explanation for that. So what is the value of y when x is 0? You get it? Because that is the interpretation of the y, the intercept on the y-axis. Like here, x is 0. So the y value here is the intercept on the y-axis. Did you study mathematics?
Hello.
Yeah, I'm asking him. Is he a mathematician?
He's a physicist.
Okay, so he's a mathematician.
Yeah, and another
Okay.
way you can also interpret the intercept is an offset, okay? You see, when we have a gradient, we can have it in different points, okay? A typical one, a trivial solution would be when it is passing through the origin, right? So your y kind of gives it an offset. So the y intercept.
This is what Eric is basically saying. I can draw two lines with the same gradient, but I started from a different point, but they have the same gradient. So the intercept gives it a fixed point to start it from. Do you get it? Okay. All right. So how should this guy come up with finding m and b? Well, it will first of all give an estimate. So f prime is an estimate. We have given it y. Our y is actually the degree Fahrenheit. Then it will estimate. But how will it estimate? It will randomly initialize m and b. It will choose any value. You say, dude, I don't care. M and b could be any value. Let me assume that m is 0.1, b is 5. The beauty of this gradient descent algorithm is no matter where these values start from, thanks to calculus, we will always get there. Okay? Okay. So now it has an estimate. But you see, for every C, C1, F1, C2, F2, like what I mean is for every degree Celsius, there's a corresponding degree Fahrenheit. Okay? So the model has to calculate what is known as a loss. And here again, this sigma thing we are learning. What do we do with sigma? What do we do with sigma? Welcome to sigma. From I equals 1 to m, I will explain this formula to those of you who feel like crying. MC plus B minus the actual F squared divided by 1 over m. This is known as the loss. Let me go to a new page, write it there, then we can spend time on it. So I'll say loss is equal to sigma I starting from 1 to m. Then we have our, let me make sure I'm writing it the same way I wrote it, MC plus B minus F. So MC plus B minus the F all squared. And then we multiply that by 1 over 2m. Some people also make it 1 over m. It doesn't really matter. This brother here is called the mean squared error. You see, the model starts by making an assumption for m and b. So for each degree Celsius, over here is going to be CI, BI, CI, FI. The I is a row. So I wrote it like this. We have a degree Celsius, a degree Fahrenheit. So there's row 1, row 2. This is supposed to be F. This is also F. So F2, C3, F3, dot, 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 CM. F, M, dot, dot, dot. So the M is the number of rows. That is what we usually use to denote number of rows in a data set in machine learning, M. So for each of the rows, it is going to assume that, yeah, M is 0, B is 0. Now for each of the rows, let's calculate our F prime. Our F prime is our estimate. And this loss function here helps the model to calculate on the whole data set, how much loss am I making? The lesser the loss, the better the predictions it is going to make. The lesser the loss, the more quality the estimation of M and B are. As a matter of fact, in linear algebra, there's a definite formula for solving this without this iterative process. But computationally, the iterative process is better than the linear algebra one, because if you have 1 million by 1 million matrix, multiplying that, even with a GPU, you struggle. But the iterative process is less computationally intensive. So it is going to iteratively make changes to M and B. That is where Eric was saying, is it brute force? It's not. Tomorrow, when I show you linear gradient descent, you will see that there is a definite way that we can use that. You can even apply gradient descent in your own solution. It's not just machine learning. Whenever you are searching for something, and it's a very smart, beautiful application of calculus. So it is going to iteratively do this and calculate the loss on the entire data set. And with the help of calculus, it will let the model know in which direction it should descend. I'm not going to prove, but because of the square here, first of all, who knows why we are squaring it? I can write this formula this way too. My loss is equal to 1 over 2m sigma I1 to m f prime minus f squared, because f prime is equal to this guy. That is the estimate. So the model gives its estimate. It looks at the actual value, but why are we squaring it here?
Yeah, hello.
No, Eric, I don't want you to answer.
Yes, sir.
Okay, now Eric, you can answer.
Is it for absolute values, right? So that we can ignore negative numbers.
Yes, because we don't care in which direction we are making the error. See, if we don't square it, if for one instance, I made an error of -5 in the prediction, and in another, I made an error of 5, they will cancel out, and it will look as if the model is doing well. You see, if I add these, I get what? 0. So it will feel as if the model is doing well. So we care about the magnitude of error without in which direction. You see, if it is negative, it means it is predicting a smaller value. You see, if it is f prime minus f, then it means that when f prime is small. Yeah, Mohammed, you have a question?
Okay. I have to leave, guys. So many thanks for your time.
Okay.
Yeah.
All right, fine.
I catch you
So,
tomorrow.
Okay. So if f prime is smaller than f, then this subtraction is going to be negative. But if f prime is bigger than f, then the subtraction is going to be positive. But we don't care so much about the sign as much as we do about the quantity, the magnitude itself. That is why we square it, so that whether you are negative or positive, we get the actual thing. Then we divide it by m because we want to find the average error. So if I have m numbers, I sum them or divide by m, then I'm getting the average. The reason why some people do the 2 here is when we start talking about the calculus, the 2 here will cancel out the square here and to make the derivative calculation very simpler. Because you see, if we are calculating the derivative of this, for those of you who remember, 2 will come and multiply 1 over 2m, right? And then these guys continue. So this cancels this, and then it makes the derivative calculation simpler than if there is no 2 here. And this is mathematics. As far as the patterns are still in there, it doesn't matter. So, ladies and gentlemen, this, I don't want to bother you so much with the calculus today. I want us to get to this point, then we can have fun, because already I'm sure some people are giving up. But when you go to my YouTube, I actually explain everything in details with the formula, how it is working, just as I've done, but into more details. And I even show how to code this formula, which I will do in one of the days within the week. So once it has this, it iteratively does this, always nudging M and B. Now, let me show you how it does the nudging. Because of the square in the formula, if you plot your loss, let's say we choose one of the parameters, okay? So we plot the loss on the x-axis, and we plot, let's say, the M on the y-axis. Because we have a square in there, we are going to get a concave graph like this. Okay, so we have two graphs. Then it also plot, it will make the same plot for the loss against the B for both parameters. Because of the square, we'll get something like this. Now, if you don't get a convex loss function, you can't apply machine learning. Why? Because it is possible for us to use calculus to find the lowest point. You see, this is a graph of sorry, I swapped them. It's actually supposed to be the M here against the L, and then the B here against the L. So we are finding out how changing M affects L, how changing B affects L, and we are interested in the value of M that will give us the least L, and the value of B that will give us the least M. And for those of you who understand calculus, the lowest point of this graph is where? It's here, right? It's at the point where the gradient is 0. So at this point, the gradient is almost 0. And it's the same for the B. So when it combines these two, then we are going to get a 3D plot that looks like this, something like this. Because now we are plotting L against M and B. So it is the work of our model to find how should it go until it finds the lowest point. The lowest point is here. So then it becomes the projection onto the M, the projection onto the B. The values that are at this point in 3D space is what is going to give us the lowest L. So in this case, our model can start anywhere. It can start from here. That's why it's called gradient descent. It is using gradient calculations to descend a hill. It is interested in finding the lowest point of the hill. Let me show you, let me give you an intuitive understanding of how gradient descent works. You are a human being. I have placed you on top of a hill. In fact, it's a place of mountains. And I've put you here. Okay? Then I've blindfolded you. Then I've told you that I have put $10 million on the flat area of the land. Go there and get it without taking off the blindfold. How will you do it? As a human being, you should be able to do it. You will feel the terrain with your leg. Then you will move in the downwards direction, right? But you will not take big steps as you would do if you were not blindfolded, because somewhere could be a trap. So in tree, you feel and then you move small, but you are always going to move in the downward direction. Whenever you feel you are climbing up, you know you are moving away from your $10 million. But as you go down, and how will you know if you have gotten down? Because there is a chance that you will get here. Then you took a big step, then you came here. How will you know that you have crossed the level path? If you cross the level path, you begin to go what? Up. So then common sense will tell you that begin walking down. So the place you concentrate is the place where you come down small, you're beginning to go up. You come down small, you're beginning to go up. Then it means around this area, take baby steps here. And this is the area where you will find your $10 million. So you see, mathematics is not a waste. And how do you 10 million when you are blindfolded? It's never a waste. So the algorithm, which I'll show you in another meeting, will iteratively nudge M and B, small. It is important that it nudges them small. So we use something called learning rate to control that. You will see that learning rate, which is usually also known as alpha in machine learning. Because you see, if it started from here, then it jumps here. Then it realizes I'm going up. Okay, let me come down. Then it jumps here. It realizes I'm going up. Let me come down. Then you see that your model will do this. So when the model finds the lowest point, we call it convergence. Convergence. That means it has converged. When it converges, it means the loss is smallest, the smallest possible. And when your loss is, because look at the calculation of the loss. So when you get a small loss, it means you are making good enough predictions. So this is the intuitive understanding I'm giving you to understand how the learning is happening. Then God willing, tomorrow I will show you how to implement gradient descent, a simpler version of it in Python. So I'm going to take questions. We have 5 minutes. I'm going to take questions before we end.
Yeah, first question.
Yep.
Yeah, I remember in optimization, is my mic on? Yeah. So I remember in optimization, we do something like this. We call them minima and maxima. I think even in
local minima, local maxima. That is exactly it.
Yeah. Yeah. So there are times that we use the maxima, right? So in machine learning, do you also have an application for that? Maybe gradient ascent or something like that?
There is gradient ascent, but it's not usually used in machine learning because gradient ascent is when you are looking for the highest point of something. But machine learning is focused on reducing the loss.
The loss, okay.
So you use gradient ascent or you find the local maxima. And we like the local maxima because you see, sometimes your graph surface is going to look something like this. And then when you find yourself here, this is not the local minima, because this point is higher than this.
Yeah.
So there are techniques, there are several techniques called regularization, where even if you feel you've gotten to a lowest point, we can mathematically nudge the movement. And if it is possible that we see you have climbed, then dude, it was probably not the lowest. Then you come down, then we nudge, but you realize that when you are at the local minima, your nudging is going to be centered around a particular place. Then you know that you have found it. So machine learning is mostly concerned with local minima. But when you go to things like reinforcement learning, we are trying to maximize reward. That is where we are interested in the local maxima.
Okay.
What do we do with calculus? What do we do with calculus? This is what we do with calculus.
Well, actually, I think sometimes it depends on from the angle that we look at it. Because for me, I remember for the first time we did calculus in SHS, you know, the analogy where from the first principles, you know, how the teacher took it, I got to get some understanding that it's really meant for something that has to do with data. But I hadn't gone deep into it, so I didn't find it trivial anyway. I felt that. So it depends on, you know, the student's own perspective, I think.
Yeah, I think I have this book. Eric, you didn't remind me yesterday. I'll share a couple of books with you. There's a book called Calculus Made Easy. It teaches calculus in a fantastic English approach, and you will appreciate it. I'll add it to my set of books and then share it.
There is another one, Calculus Lifesaver, a very beautiful book.
Okay.
Very beautiful book.
Lifesaver.
Yeah, it's a very beautiful
I have, yeah, so I have these books, power books. These are all my powerful books, very Very, very powerful books. Math for Programmers. This teaches you linear algebra from a programmer's perspective using Python to let you understand there's no bullshit algebra and all these things. Eric, please give me your email. Chat it to me and let me share with you before this, this thing ends. So chat it on the Zoom thing. Then let me just
share. I'm trying to.
The last time I shared this folder with some Ghanaians, I don't know why people are wicked. They came into my folder and they cut things instead of making copies. Like, people are very sinister. I have bought my books, I've shared with you. Just come and copy.